Well, welcome to the derivatives as a rate of change. I'm going to go through these notes as an introduction, but you've seen some of this before, but just to kind of review. And we're going to talk about motion and derivatives. If I had S equals f of t, and t always usually stands for time, and S is our position, so this is our position function again. Okay, so if I had a point, it would be the point TS. If I was going to graph that, you'd have your time on your x-axis and your position on your y-axis, and that would be your position function. Here's our velocity function. Again, the velocity, or the instantaneous velocity, is the derivative of a position with respect to time. That is why it's always ds dt, okay? Or it's s prime of t, it's the first derivative. If a body's position at time is s equals f of t, then the body's velocity at time t is this, which is the first derivative. This goes back to our definition that we talked about before of the derivative, is the limit, and we're talking about the change in time. Now, speed is the absolute value of velocity, meaning or the absolute value of ds dt. Remember, velocity is a vector quantity, and a vector quantity has direction and magnitude. Well, if I take the absolute value of this, it's always going to be positive, so the direction doesn't really matter for speed. It's the same value, but this is always the positive value of velocity. So if I drive to someone's house, say, they're not going to mind the direction doesn't always matter. Not one way is negative, not one way is positive, but you're going to want to know the speed that it took to get you there. Okay? Whoops, I skipped something here. All right, now let's talk about acceleration. Acceleration is the derivative of velocity with respect to time. If a body's position at time t is s equals f of t, then the acceleration is the derivative of the velocity, or the second, excuse me, the second derivative of position. So a of t is the derivative of velocity, or the second derivative of your position function. Now this should all sound familiar because this was in an earlier video on the power functions. Jerk, again, is the derivative of acceleration with respect to time. So jerk is the third derivative of your position function, or the derivative of your acceleration. So j of t is the first derivative of acceleration, the second derivative of velocity, and the third derivative of position. Now, what do derivatives tell us again? Well, if my first derivative is positive, then I know my original function is increasing. Okay, so this is positive. My original function is now increasing. If my first derivative here is negative, then I know my original function is decreasing. This should be all review, but it doesn't hurt to kind of go over it again. So this would be a decreasing direction. Remember, the second derivative is the rate of change of the rate of change, so your slopes will change. That causes a function to curve. So since f double prime is a derivative of f prime of x, when f double prime is greater than 0, my derivative is increasing, and this causes my original function to be concave up. And we talked about this, concave up like a cup. Okay, so this is positive. When our second derivative is negative like this, that means my first derivative is decreasing, which causes my original function to be concave down like a frown. Okay, On the bottom here, I have a chart that should look familiar to you. So I'd like to go through this one more time with you. So here's our first derivative and our second derivative. Our first derivative has to do with increasing or decreasing of my original function and of my original function concavity. Okay, so it's either concave up or down depending on what the derivative is. Okay, so if they're both positive, I'm going to do this in quadrant 1. That means my function, my original function, is increasing and it's concave up. So it would look like this. The second one is, I'm going to do a graph in quadrant 1, that if my first derivative is positive, which means my function is increasing, and this is concave up. Let's put this here first. Here it means my function is increasing and it's concave down. So if it's increasing and concave down, it's going to kind of look like that because my slopes are decreasing. Here, these two, my function is decreasing. This is concave up and this is concave down. So this is what my graph would look like. So if it's decreasing and it's concave up, it kind of looks like this. If it's decreasing and concave down, it would look kind of like this. So there is a little introduction and review for what we did before. Now we're going to talk about a particle moving across a coordinate plane. Now the only thing with this page is I've got all these things we got to fill in up here, and we're going to be referring to this picture a lot, okay? So I'm going to go up and down a lot. I apologize for that, but you've really got to look at this, all right? So we're going to talk about it, then I'll go up and fill it in. So here I have a graph, and this graph is at v equals f prime of t. So this is the graph of the derivative. So this is a velocity graph. Okay, I want you to think about that. So here's 0, and if I'm above the graph and it's velocity, all right, that means my particle is moving forward. All right, so I'm going to have to pick a different color here. Well, it's too dark. So let's undo what I did there. Okay, so if it's greater than 0, my particle is moving forward. And again, over here it's moving forward because the graph is above the x-axis. If I'm below the x-axis, okay, that means my particle, because you have to show direction with velocity, so the only way you can show it is if it's negative, that means it's moving backwards. And if you look down here, this means I'm moving backwards if I'm below. All right, so I want you to keep that in mind because all down here, all the numbers are negative, so that means my particle is moving backwards, okay? So, if I were to look at this during the first 3 seconds, from 1 to 3, right here, you can see that this particle is moving forward, okay? It's speeding up here because it's increasing. It stays constant here, so it stays steady, and then it's decreasing, so it's slowing down. That's what's happening the first 3 seconds, okay? Then between 3 and 5, notice my particle is going backwards, okay? It's going backwards for 2 seconds, all right? Then it stands still for 1 second because my velocity is 0, so it's not even moving. So here it's moving forward, it speeds up, it's constant, slows down, then it goes backwards for 2 seconds, and then it stops. Is what's happening here. Then it's speeding up for the last 2, and then it's moving forward again. So let's kind of fill in what's going on here. So here we go. The particle moves forward for the first 3 seconds. The particle moves backwards for the next 2 seconds. And it stands still for 1 second. The particle achieves the greatest speed at, now let's figure out where it's at the fastest, okay? And it looks like here it's speeding up and it's constant here and it's slowing down. Now even though this is backwards, because he is going backwards, it looks like the greatest speed, because because he's speeding up here, but it's in a different direction, is right here. This looks like the greatest speed right here. Okay? So it looks like at 4 seconds, it's going the fastest. It just happens to be going backwards. Okay? So the particle achieves the greatest speed at 4 seconds. The rate at which the body's velocity changes is the body's acceleration. So if your velocity is changing, this is an important concept. Okay, the rate of your velocity, it's the next derivative, that's of course acceleration. Okay? The blank measures how quickly the body picks up speed or loses speed. That is acceleration. The sudden change in acceleration is called jerk. That's the fourth derivative. When a ride in a car or a bus is jerky, it's not the accelerations involved are necessarily large, but the changes in accelerations are abrupt. Okay? So that kind of goes through that. Well, there's a beginning of how we're going to talk about derivatives in movement, and that ends this video.